I want you to imagine for a second that you are standing in a chemistry practical lab.
Okay.
You're holding a test tube or a beaker, and inside is a clear solution. It's vanadium. Now, usually things are a bit boring. No. Clear liquids, maybe a white precipitate.
If you're lucky, yes.
But watch this. You add a specific chemical, and that clear liquid turns green. You add something else, it shifts to this deep blue. You tweak it again, and suddenly it's bright yellow. It's cycling through a rainbow of colors right there in your hand.
It is quite a spectacle, isn't it? And if you tried that with, say, a beaker of sodium chloride?
Nothing.
Absolutely nothing. You could stare at it all day. Sodium stays the same. It doesn't change its costume. But vanadium, it wears many masks.
And that is exactly what we're unpacking today. How can one single element wear so many different masks? Welcome back to the deep dive.
Today we're focusing on Unit 4, the D and F block elements.
And specifically, we're going to master the general properties of the transition elements.
This is such a crucial topic, a real heavyweight for the board exams. But before you think this is just about memorizing a list of colors...
For the practical Viva.
Yes, exactly. Let's talk about why we actually care.
Right. Because usually properties feels very abstract. You're saying this is practical.
Extremely. The iron in your hemoglobin carrying oxygen through your blood right now, that works because of these D-block properties.
Wow, okay.
The industrial catalysts making fertilizers, the pigments in paints, the alloys in your car, it all comes down to the unique behavior of the D-block.
So we're talking about the multitaskers of the periodic table.
That's the perfect word for them.
So let's start at the zero level. How do we explain this to someone who just finished Class 11 with S block and P block fresh in their minds?
At the simplest level, you have to look at their job description.
Okay.
Think of main group elements like sodium as people with a very fixed job title. Sodium is like a worker who has one role. It's always +1. It never, ever changes.
So sodium is the guy who does exactly one task. Reliable, but not very flexible.
Precisely. Now, contrast that with transition metals. These are the highly skilled workers of chemistry, the multitaskers. They can switch roles.
So iron can be +2 in one situation.
And then switch to +3 in another. It adapts to the environment.
Okay, that makes sense. But wait a minute. Does that mean every element in the D block is a multitasker? Because I remember seeing zinc there. And I don't recall zinc doing anything colorful or fancy.
That is a very, very sharp observation. And you've just hit on one of the biggest traps in this unit.
Oh,
We call that the zinc imposter. We will definitely get to zinc in a bit, but just keep that thought. Not everyone in the D-block neighborhood actually behaves like a true transition metal.
Got it. Zinc is the neighbor who doesn't fit in. So for the real multitaskers, what allows them to be so flexible?
It's all about accessible skills. Let's use an analogy. Imagine a busy hotel kitchen.
Okay, I'm visualizing it. Pots banging, lots of noise.
Right. Now, the main group elements,
Yeah.
your S and P block, they're like the specialized staff.
Yeah.
The dishwasher only washes dishes.
He's a specialist. Rigid.
Exactly. You ask him to cook a steak, he can't. But a transition metal, like iron or manganese, is the executive chef.
Why the chef?
Because the chef has a whole range of accessible skills. In chemistry, these skills are the electrons in the d orbitals.
So having d orbitals is like having a full set of professional knives and knowing all the recipes.
Yes. And because these skills are available, they can adapt. Depending on the kitchen environment, the oxidizing or reducing conditions, the chef changes roles.
Okay.
Iron can be a raw ingredient, Fe0. It can be lightly cooked, Fe+2, or fully roasted, Fe+3. It shifts. Sodium is just washing the plate.
I like that analogy. So the flexibility comes from these extra tools, the d orbitals. But let's get a bit more technical. What is physically happening inside that atom?
What's really happening, and this is the phrase you need to remember, is that these metals have partially filled d orbitals.
Partially filled. So not empty, but not completely full either.
Exactly. Because they are not full, the electrons inside are very accessible. And this accessibility leads to 5 huge consequences.
Let me guess. These are the general properties we're talking about today.
Correct. 1, variable oxidation states. 2, paramagnetism.
Because of unpaired electrons.
Yes. 3, color. 4, complex formation. And 5, their catalytic properties.
That's a heavy list. It feels like a lot of unconnected facts to memorize for an exam.
It feels that way, but they all stem from that one single idea. Partially filled d orbitals. In fact, here's an anchor definition, totally safe for your board exams.
Okay, let's hear it.
Transition elements are characterized by the presence of partially filled orbitals in their ground state or common oxidation states.
Short and sweet. It all comes back to partially filled orbitals.
It always does.
Now, can I clarify something? I think a lot of students feel this way. When I first studied this, I thought colored compounds were, rare, special.
That is a classic misunderstanding trigger. Students think color is the exception. In the D block, it's the exact opposite.
Oh, really?
Yes. All transition metal compounds with partially filled d orbitals are colored. Being colorless is actually the rare exception here. If a solution is clear, that's the weird part.
Okay, that completely flips the script. Color is the default. Now, the kitchen analogy is great for flexibility. But can we build another mental picture? Something to explain the mechanism, especially for color and complexes.
Absolutely. Let's build a mental movie. I want you to picture a transition metal atom, but instead of a ball, imagine it as a molecular stage.
A stage, like a theater stage.
Yes, exactly. On this stage, there are 5 spotlights. These represent the 5 d orbitals.
Okay, I see the stage. 5 spotlights.
Now, on this stage, you have actors. These are the electrons. And remember our core concept.
Partially filled.
Right. So some spotlights have actors, but some are empty. This is where the action starts. Because there's space, the actors can jump from one spotlight to another.
And when they jump, that requires energy, right?
Exactly. They absorb energy from visible light to make that jump. And the light they don't absorb is what we see as color.
So if the stage was completely full, every spotlight packed.
Nobody could move. No jumping means no energy absorption, which means no color.
That makes perfect sense. So color is just electrons dancing between spotlights. What about complex formation?
Well, look at the stage again. You have empty spotlights. This means guest actors from outside can step onto the stage. We call these guests ligands.
Ligands. Okay, that's a term from coordination chemistry as well. So the ligand is just a molecule that comes and sits in an empty d orbital.
Precisely. It donates a pair of electrons. It brings its own actors to the metal's empty spotlight. This is how complexes are formed.
And I'm guessing the stage analogy also explains catalysis.
It does, because the stage is so flexible, the actors can move around to help with scene changes. The metal can hold on to reactants for a split second, let them react, and then release them. It's a dynamic stage.
I really like that. Jumping actors give us color. Empty spotlights let in ligands for complexes. And the flexible stage allows for catalysis. This brings us back to what you said earlier, the imposter. Zinc. Let's apply this stage analogy to zinc. Zn2 plus like.
Okay, good. Zinc has an atomic number of 30. As an ion, Zn2 plus S, it has a D10 configuration.
D10. That means 10 electrons in the d orbitals.
Yes, and there are 5 orbitals, and each can hold 2 electrons, so.
Wait, the stage is full. Every single spotlight is double booked.
Exactly. It's a packed house. No actors can jump because there is nowhere to land. No jumping means no color, which is why zinc sulfate is white.
And magnetism.
Magnetism comes from unpaired electrons, actors standing alone in a spotlight. In zinc, everyone is paired up. So no unpaired electrons means it's diamagnetic, not magnetic at all.
No room for guest ligands either, I assume.
Not easily into the d orbitals, no. So zinc sits in the D block, but it behaves like a boring main group element.
That's the perfect way to remember it.
Yeah.
Zinc equals boring equals full D10.
Correct. And this also applies to cadmium and mercury right below it, the pseudo-transition elements.
Okay, let's talk real-world applications. Catalysts show up a lot in exam questions.
Yeah.
You mentioned the Haber process.
Yes, for making ammonia. We use solid iron as a catalyst. Now, think of our stage again. The nitrogen and hydrogen molecules come to the iron surface.
Right.
The iron uses its d orbitals to form temporary bonds with them.
Temporary is the key word there, isn't it?
It is the most important word. If the bond was too strong, the molecules would get stuck. Too weak, nothing would happen. Transition metals form bonds that are just right.
So they hold the reactants, let them react to make ammonia, and then
Pop. They release the new molecule and are ready for the next batch.
it's like a handshake introduction. Nitrogen, meet hydrogen. Now you're ammonia, goodbye.
That's a great way to put it. And without that d orbital handshake, we wouldn't have synthetic fertilizers. It's that critical.
Same with the catalytic converters in cars.
Same principle. Platinum or palladium grab toxic gases, hold them on the d orbital stage long enough to convert them into safer gases, and then release them.
So we have covered the core idea, the analogies, and the examples. Now, I want to slow down a bit.
Exam mode.
Exam mode. For the student listening, pen in hand, they need the precise answers. Let's go through the exam-safe clarity lines. I'll state the property, you give me the key phrase.
Let's do it.
First, variable oxidation states. Why?
The key word is comparable energy. You have to write, variable oxidation states arise because the N1d and N's electrons have very similar energies. So electrons can be removed from both.
Okay. Property number 2, color.
The key word is DD transition. You must write, color is due to DD transitions. If you don't write that phrase, you lose marks. Simple as that.
Got it. DDD transition. Third, magnetism.
The key word is unpaired electrons. Paramagnetism is directly related to the number of unpaired electrons, and tie it back to zinc. 0 unpaired electrons, so it is diamagnetic.
Fourth, complex formation.
The key phrase here is availability of vacant d orbitals. The full reason is their small size, high charge, and those vacant orbitals to accept electron pairs from ligands.
And finally, catalysis.
2 reasons. Ability to adopt multiple oxidation states and to form temporary bonds or complexes.
What about physical properties? They're so hard and have high melting points. Why?
That's about metallic bonding. High melting points are due to strong metallic bonding because both N's and N1d electrons participate. More electrons holding hands means a stronger metal.
Brilliant. Those are the revision notes right there.
And you notice almost every single answer points back to the same root cause.
Partially filled d orbitals.
Exactly. If you get stuck on an exam question about the d block, just start by drawing the d orbitals on your rush sheet. The answer is almost always on that stage.
So let's wrap this up with a quick summary. If a student remembers only 3 things, what should they be?
First, the core idea. It is all about partially filled d orbitals. That's what makes them different.
Second,
Remember the chef in the kitchen? They are flexible multitaskers, not rigid, single-task workers.
and third,
Beware the zinc exception. A full D10 configuration means the party is over. No color, no magnetism, it's the imposter.
you know, when you put it like that, the periodic table feels less like a chart and more like a cast of characters.
It really is a story, and once you understand the character of the D block, its flexibility, its color memorizing the facts becomes so much easier.
That is a great place to leave it. Next time you see a rusty piece of iron, don't just see corrosion. Think about the busy chefs and jumping electrons inside.
And here's a final thought. The iron in your blood is red. The iron in a sapphire can make it blue. The iron in magnetite is black.
Same element.
Same element, just with different guests on its stage. It shows you just how sensitive and beautiful this chemistry really is.
I love that. Same actor, different costume. Thanks for joining us on this deep dive. Keep asking questions and keep learning.
Goodbye, everyone. Study smart.